Welcome back to this course on stereochemistry. Today we are going to see about symmetry elements and symmetry operations. We are going to understand how this symmetry is going to determine the stereochemical outcome of a molecule. But before going into the details of symmetry and stereochemistry, let us try to understand what symmetry is. An object is symmetrical when one half is the mirror image of the other half. It may be divided by one or more lines of symmetry. For example, let us take a butterfly. If you draw a line exactly at the center of the butterfly, you can see that one half of the butterfly is exactly the mirror image of the other. So symmetry is having one side that exactly mirrors the other. A line of symmetry divides a symmetrical shape into half. So you can see all these shapes have a line of symmetry where one half is the mirror image of the other. This particular hexagon has several lines of symmetry which divides the shape into equal halves. And if you look into the word called shape, you can see if we could draw a line here, then this line does not give you two equal mirror images. Therefore, this is not a symmetrical object or shape. If you look into H and if you draw a line here, that gives you two equal half. If you draw a line here, then that divides it into two equal half. Therefore, it is symmetrical. If you take the letter A and if you draw a line here, then it divides the letter A into two equal half. And if you take P, it does not have any line that makes it symmetrical. If you take the letter E and if you draw a line here, then it divides the shape, the letter E into two equal half. So with this idea in mind, let us move on to our topic in stereochemistry, symmetry and stereochemistry. Now, symmetry plays a very important role in determining the stereochemistry of a molecule. Let us see how. A molecule is said to be asymmetric if it has four different groups attached to it. Yes, that is a thumb rule, acceptable. But there is also another important rule which says that a molecule is said to be asymmetric only if it is completely devoid of any symmetry elements. Now you can ask me, what is a symmetry element? A symmetry element is a point or an atom or a plane or a line on which some symmetry operation is performed. The next question arises, what is a symmetry operation? A symmetry operation is a series of steps, either rotating or reflecting, or the series of operations, experimental things that you do in order to ensure whether that particular object or molecule is symmetric. We will be quickly looking into the various symmetry elements and symmetry operations. A molecule is said to possess a symmetry element if the molecule is unchanged in appearance after applying the symmetry operation corresponding to the symmetry element. Okay, so we are going to see how all these things are going to happen in our molecule, but let us understand that what are the symmetry operations they are spatial transformations actually. So symmetry operations are spatial transformations that we perform with respect to a point or an atom or a plane or an axis. Okay, and it is classified into rotation, reflection, and inversion. There are three elements of symmetry that a molecule may possess. It can be a rotation, it can be a reflection, and it can be an inversion. Let us look in detail about each of these symmetry element and operation, and let us try to apply it in our molecule and understand whether our molecule possesses any of these symmetry elements. But please remember the thumb rule: if your molecule possesses any of these symmetry elements, then the molecule is not asymmetric, or in other words, the molecule is achiral. It cannot be chiral. The first symmetry element and the corresponding symmetry operation is rotation. The symmetry element is a simple axis of symmetry represented as C subscript n. And when a molecule is rotated by an angle of 360 degree divided by n around an axis, and if you get an arrangement similar to the starting molecule or the original, then the molecule is said to possess a Cn axis of symmetry. And the operation, when repeated n times, it gives the exact original. Now, the proper axis of rotation Cn, n corresponds when n is equal to 1 if you perform a 360 degree rotation. Please remember, all molecules will have this axis of symmetry, which is n is equal to 1. Because any molecule, if you rotate it as it under 360 degree, you will end up with the same molecule. And if n is equal to 2, then the molecule is said to have a 180 degree, or in other words, if you rotate the molecule 180 degree and if you get the exact replica of the starting molecule, then the molecule is said to possess C2 symmetry. If you perform a 120 degree rotation, 360 by 120 is equal to 3, okay, or 360 by 3 is equal to 120. So you end up with the same molecule, and you can say that the molecule is said to possess a C3 symmetry. And if you rotate the molecule 90 degrees, you say the molecule has a C4 symmetry, and 60 degree C6 symmetry, and infinity, any degree rotation, then the molecule is said to have an C infinity axis. Okay, and what is the principal axis of rotation? See, a molecule can have many axes of rotation. Okay, a single molecule can have a C2 axis, C3 axis, etc. But the n highest order, if a molecule has C1, C2, C3 axis, then the C3 axis is said to be the principal axis of rotation. And we need to remember that Cn, which has the n value which has the highest order of the axis present, is what we call it as a principal axis of rotation. Let us take an example. Let us take this molecule, which is methyl chloride. Now, this methyl chloride can have an axis which passes through the chlorine atom, and if you rotate this molecule at an angle of 120 degree, you can see the hydrogen which is present originally here moves here. You end up with the same kind of molecule. Again, if you rotate this molecule with an angle of 120 degree, you can see the hydrogen with a blue color comes over here, and you end up with the same molecule. If you again rotate the molecule 120 degree, you get back the starting molecule. So this molecule possesses two axes of symmetry. One is C1 that is present in all the molecule, but and along with that it also possesses C3 axis of symmetry. So after 3 rotation of the molecule around C3 axis through chlorine, we get the original arrangement. Therefore, this molecule cannot be asymmetric because it has a C3 axis of symmetry. Let us move on to our next symmetry element, and the corresponding symmetry operation, which we call it as a plane of symmetry. What is a plane of symmetry? A plane can be considered as a mirror. Therefore, we normally call it as a mirror plane. So, a plane which divides the molecule into two equal halves, thus the two halves of the molecule are the mirror image of each other, then the molecule is said to have a plane of symmetry. There are two types of this plane of symmetry or operation. One is called sigma h, and we call this as an horizontal plane. The other one is called sigma v, and we call it as a vertical plane. If you take up an ethene molecule, and this is actually a dichloroethene, but let us say we have an ethene molecule, and if you pass a plane, you cut the molecule using an horizontal plane, the molecule divides the ethene molecule into two halves, and the molecule is said to have a horizontal plane of symmetry. In the case of chloromethane, if you pass a plane in such a way that the chlorine and hydrogen are present on the plane, and this is called a vertical, because you can see this plane is not on the axis in which these two hydrogens are present. So if we say the axis in which the plane is present is y, then the two hydrogens are present in x. Therefore, if you put a plane where it can pass through your molecule, and if you end up with mirror image of the atoms, so this molecule is said to have a vertical plane of symmetry. So a vertical plane divides the chloromethane molecule. So any molecule with a plane of symmetry or a center of symmetry must be achiral. So a plane of symmetry is any plane cutting through the molecule such that one side is a perfect reflection of the other. If we take up this particular molecule, and if we put a sigma v, that is vertical plane of symmetry, you can see this part of the molecule is exactly the mirror image of the other. So you can see this. So, and therefore, even though this particular molecule has two chiral carbon, so this is a chiral carbon and this is another chiral carbon, but still this molecule has a plane of symmetry. So the molecule is not chiral. Even though it has two chiral centers, it is said to be in a meso form. The molecule is said to be a meso form. Let us consider another molecule. Let us take 1,3 dimethyl cyclohexane. You can see a plane passes exactly across the center of the molecule, and the plane divides an object into two symmetrical halves, and this is what we call it as a plane of symmetry. And this particular molecule is not said to be a chiral molecule. A compound which does not have a plane of symmetry is called an asymmetric compound. So a molecule should not have any plane of symmetry, and then it is called an asymmetric compound. But what is a dissymmetric compound? A dissymmetric compound is one which can have a simple axis of symmetry, but it should not contain an alternating axis of symmetry, which we will be seeing very shortly. And a dissymmetric compound is the one that cannot be superimposed on its mirror image. Let us see what is center of symmetry. Let us take this molecule. Now in this molecule, if we can choose a point such that if an atom is joined to it and this line is extrapolated to the other side, we find the same atom. For example, from here, if we draw a line, and if line touches this carbon of the carboxylic acid, and if we draw a similar line just in the opposite direction, again we end up with a carbon which in which we have a carboxylic acid group. So if such a situation arises in the molecule, then we say this particular molecule has a center of symmetry, or we can say it is a point such that we would find the same atom or group in either direction at equal distance. So in the above isomer of tartaric acid, the dot is exactly at the same distance from two hydrogen. Similarly, we can draw a line to this hydrogen, and we can also draw a line to this hydrogen, and we end up with the same atom. Or two OH, if we could draw a line to this OH, and if we could draw a line to this OH, then we end up with the same atom or group. Therefore, this particular molecule is said to possess the center of symmetry. It is denoted by I. And this is called inversion. And what is an alternating axis of symmetry? Now, an alternating axis of symmetry is represented by the symbol Sn. In this case, we have to perform two operations. If a rotation by 360 by n is followed by a reflection, so we have to do a rotation first. If a molecule is taken and if we perform a rotation, and after the rotation we have to do a reflection. Reflection is something you show it in the mirror, okay, or you place a mirror and you reflect. Okay, so what we do, we are going to do a rotation. You can see here we are rotating this molecule along this axis 180 degree. When you rotate 180 degree, this COOH group comes over here at the bottom. These two, hydrogen and OH, moves to the top. On the other carbon, the COOH comes at the top, and we have two OH and hydrogen at the bottom. Then we have to put a reflection plane. We have to put a reflection plane. When you put a reflection plane, exactly a mirror. See, it is something like you are placing a mirror here. So when you put a mirror here, you can see this COOH will be reflected at the top, and this OH is reflected here, this hydrogen is reflected here. On the other carbon, you can see this OH is reflected at the top, okay, and this hydrogen is reflected, and similarly this COOH is reflected down, and this molecule is nothing but the starting molecule. So if your molecule is made to undergo a rotation at a particular angle, followed by a reflection in a plane perpendicular to the axis. So it has to be a plane perpendicular to the principal axis, and it gives the original arrangement. Then the molecule is said to have an SN, that is alternating axis of symmetry. A dissymmetric molecule is something that can have a simple axis of symmetry, but it should not contain alternating axis of symmetry, and such molecules are said to be dissymmetric in nature. So alternating axis of symmetry corresponds to rotation plus reflection. A carbon atom which is bonded to 4 different groups or atom is called a chiral carbon or an asymmetric carbon. And a very important condition apart from this is the carbon or the molecule should be devoid of any symmetry element. Okay, and if the molecule is only devoid of any symmetry element, then we call that molecule as an asymmetric molecule and the carbon as asymmetric carbon. Let us see some of the checklist for testing the chirality in a molecule. The first test is we need to draw and see the mirror image of the molecule, and we have to check whether the two molecules are same or different. If they are different and if they are non-superimposable mirror image, then the molecule is said to be chiral. If they are the same, then it is not chiral. So let us take this particular molecule and let us try to draw the mirror image of the molecule. And when we try to draw the mirror image of this particular molecule, okay, and if we see that the molecule and the mirror image are totally different, but it is exactly the mirror image and non-superimposable, then we can say that particular molecule is chiral. Test 2. If the molecule has only one chiral center, then certainly the molecule will be chiral. But if the molecule has more than one chiral center, like our tartaric acid, it is most likely chiral, but the exceptions are meso compounds, which have the chiral center but are not chiral due to the presence of a plane of symmetry. Please remember, it is only this plane of symmetry that ensures the molecule as a meso compound. So all meso compounds will surely have a plane of symmetry, and if a molecule has a plane of symmetry, then certainly the molecule cannot be chiral. Now let us take this molecule 3, which has only one chiral center. Therefore this molecule is chiral. And note that in this depiction we have not specified if the NH2 group is present towards us or away from us, which means up or down. This means usually that the racemic mixture of the two. However, the molecule is still chiral even if it is in a racemic form. On the other hand, in the case of molecule 4, this molecule has two chiral centers, therefore it is more likely to be chiral. And if we apply test 1 and 2, we find that it is in fact chiral. However, if the two methyl groups are present on the same side, say for example, instead of wedge representation, if the two methyl groups are present like this, then ultimately this molecule will have a plane of symmetry, and therefore this molecule would be achiral and a meso compound. Test 3. If a molecule has a plane of symmetry, then the molecule is not chiral. This is probably the easiest test to apply, and it works for almost in all the case. Now let us take this molecule which has a plane of symmetry, therefore the molecule is not chiral. If the NH2 and OH2 groups were present in cis, there still would be a plane of symmetry and the molecule would still not be chiral. In the case of molecule 4, it does not have a plane of symmetry, therefore the molecule is most likely to become chiral. Molecule 3 does not have a plane of symmetry, therefore the molecule is most likely to be chiral. It may look like there is a plane of symmetry in the plane of the page, but we have to remember that NH2 group is either up or down, which breaks the plane of symmetry, and we have not depicted the correct stereochemical projection of NH2, therefore it is most likely it is to be chiral. Let us try to understand how to assign configuration to a chiral molecule. We can specify the configuration by using the R and S system prescribed by Kahn-Ingold-Prelog system. So the famous Kahn-Ingold-Prelog system or CIP system is otherwise called as RS system. Now how to assign priority for a given atom or group in a chiral carbon or in a chiral compound. Now we have to determine the priority of the group attached to the chiral carbon. Rule number 1. Each atom bonded to the asymmetric carbon is assigned a priority based on the atomic number. The atom having the highest atomic number gets the highest priority. In this case, we know iodine as the priority number 1 and bromine as the priority number 2, chlorine as the priority number 3 and fluorine as the priority number 4. Okay, so the first thing in the assigning configurational nomenclature to a molecule, the first thing that we need to do is we have to check whether the molecule is chiral by applying all the 4 rules that we have discussed so far. Then we have to assign the priority for the groups or atoms attached to it. In the case of isotopes, the higher atomic mass isotope is assigned the highest priority. For example, deuterium gets the highest priority when compared to hydrogen. Rule 3. If the first atom or groups are bonded to the asymmetric carbon are same, then the next set of atoms has to be considered and assigned the priority. Now in this particular example, we can see in group 3 and 2, we are ending up with same carbon atom. But therefore what we need to do is we have to check for the next connected atom. In the case of this carbon, it is connected with hydrogen, whereas in the case of this carbon, it is connected with another carbon and hydrogen. Therefore, this particular ethyl group gets the highest priority. Okay, so in this case it is very obvious. Chlorine gets number 1, ethyl group gets number 2, methyl group gets number 3, and hydrogen gets number 4. Rule number 4. In the case of double bonds and triple bonds, the atoms participating in the double or triple bond are considered to be bonded to an equivalent number of similar atoms by single bond. For example, if you take a carbonyl group, we have to see that this carbonyl group is equivalent to a carbon which is attached with one oxygen. It is also attached with another oxygen, and one of these oxygen is attached with another carbon. Okay, so this is how it has to be represented and counted. Similarly, in the case of our C triple bond N cyano group, we have to see that carbon is attached with 3 nitrogen and one of the nitrogen is attached with 2 carbon. In the case of double bonds, we have to see each carbon is attached with 2 other carbon and each carbon is attached with 2 other carbon. We have to ensure that. Okay, so this is how we have to give the prioritizing in the atoms that is participating in the double or triple bond are considered to be equivalent number of similar atoms by single bond. That is, atoms of double bond is duplicated and atoms of triple bond is triplicated. After prioritizing the atoms and groups using the above rules, we can proceed to assign the configuration. Let us take this first example. So let us first prioritize the atoms and groups using the above rule. So iodine gets number 1, bromine gets number 2, chlorine gets number 3, and fluorine gets number 4. Okay, and we have to position the lowest priority group down in the case of Fisher projection and away from the observer. And this can be done by interchanging the groups. We have to remember always that interchanging any pair of groups in a Fisher projection inverts the configuration. I repeat, we have to remember that interchanging any pair of groups in a Fisher projection inverts the configuration. Say for example, if you have an R isomer, if you simply interchange one pair of group, you will end up with an S configuration. Interchanging 2 pair of groups retains the original configuration in a Fisher projection. Now after interchanging, we get this particular position. Okay, now in this case you can see we have to specify the direction of decreasing priority of the 3 groups. Now please remember, we have a structure in such a way that the fluorine is moving away from the observer. Okay, and we have iodine at the top, bromine here, and chlorine, and we are moving in the clockwise direction. Therefore we designate it as R in